Hi, class. We're going to talk about probability. And if you look in the book, now remember, just a reminder, and I'll probably try to remind you on all of the videos, that when you look at the books that I'm using, they may or not be the exact edition or textbook that you're using at the present time. And I use these videos for several different types of courses and have used these at sometimes at other semesters and so on. And things change and update, and we go to new editions, and there's changes. So again, so I don't have to always redo all of the videos. I just try to pick the best material, the best, in this case, textbook that helps me talk about the material that you need to know for the next exam. And that's what we're doing here is going on all those new concepts that'll be on this next exam. And the bulk of it is on probability. So when we start, uh, I'm going to look at the tentative schedule here. And again, let me remind you that the schedule, these dates may or may not be for the term that you're in, but the content is the same. So uh, I want to show you how to read this. So you had an exam, exam one on descriptive statistics, and then now this material that's listed on the tentative schedule from after the exam one up into the next exam, exam two, whenever that is. Again, these dates may or may not be the dates on your syllabus. You go to your Canvas page and pull up your syllabus, and you'll see the correct dates. And again, I'm just using this particular one to help me talk about what's on the next test. Well, sections in your current text, e-text 41, 42, 43, 44, 51, and 52. And these are the topics that we'll be covering. So overall, we start out with basics of probability, and then we're going to talk about the addition rule and multiplication rule. Two very, very important rules in basic probability. And then we'll talk about complements and conditional probability. We're not going to do any problems using Bayes' theorem. I'll mention Bayes, but he's just kind of a newer age probabilist that wrote some of his own books on it, and he's got some interesting ideas. And so a lot of people like Bayes, and he usually makes it into the textbooks. But we're not interested in Bayes' theorems in statistics in what we do. So then for 4.4, then we're going to talk about counting. So we're not going to be able to get through all of that stuff in one video. We'll see how far we get. Maybe the first couple sections, then we'll do another video on the last two. So we're going to go ahead and get started. And basics of probability, I don't even know exactly what the basics are, but in terms of statistics, remember that statistics we say is probabilistic modeling, and basically just means that as we try to build models of situations, they're going to involve a probability component that's related to error. So we know in statistics that we have populations that we want to try to talk about, and then we use the sample data to talk about the population characteristics. And when we do that, we know that there's going to be some error involved in that. So we need to be able to model that in. We have to be able to say, listen, how likely is it that these numbers that we came up in our sample are very, very close. We talk about confidence intervals and things, and uh, so what we want to do, and before we get into that idea of confidence intervals and probability distributions and inferential statistics, we need to talk a little bit about how probability, these basic concepts of probability, are used in statistics. And you might be surprised that uh, these traditional thoughts, we don't use much of this at all. Okay. And there's a lot of good reasons for that. So, when he talks about the role of probability in statistics, that's our focus. What probability, we're not teaching you probability. This isn't a probability course. It would be very differently taught. And in fact, it would be much, much more difficult. But we're just going to look basically at the ideas and then see what is useful for us in statistics. And so I'm going to get down to the bottom of the page here, and it says definitions. So we always have definitions we need to learn. And this one says an event is any collection of results or outcomes of a procedure. So we think of things as occurrences or events, or you could think of trials, things that are happening and things that are randomly happening. So it's not systematic where we know exactly what's going to happen on every event or every trial. We have an idea of what might happen, and we talk about that, and then we try to assign some probabilities to those things that may possibly happen. So again, we don't know exactly what's going to happen. We know what are some of the things that might happen, and we also know um, what the likelihood of those things would be occurring. So a simple event's an outcome or event that cannot be further broken down. And a sample space, okay, we'll talk about that a lot. It lists all the possible things that could occur on any given single trial. Okay, so now he says simple events and sample space. So it says simple event with one birth, the result of one girl is a simple event. And the result of one boy is another simple event. They're individual simple events because they cannot be broken down any further. With three births, the results of two girls followed by a boy is a simple event. When rolling a single die, the outcome of a 5 is a simple event. But the outcome of an even number is not considered simple because even numbers can be broken down into further pieces. Okay, well, so the sample space, right, consists of 8 different events when we talk about 3 births, right, 3 births, and what are all the things that could occur. So this sample space, what he's talking about is listing out all of those things that could occur in 3 births. You could have 3 boys. First birth could be a boy, second birth could be a boy, third birth could be a girl. And then you see boy, girl, boy, boy, girl, girl. These are all the things that could occur in 3 given births. So these are some of the basic ideas of this sample space approach to probability. And he says that, probability has been around in some senses for a long time, but there hasn't been agreement totally ever on how we should proceed with probabilities. And we probably never will. But it seems strange that in like a mathematically related discipline that could be like that. But again, what we just need to remember, we could spend a lot of time talking about these different theories and all that. But what I want to do is kind of break it down. And he talks about, he has 3 common: relative frequency approach, And there's a classical approach and then the subjective approach. All right, so let me put this down here for a minute. And I just want to talk about that for a minute. It's, we're going to focus on the things that are important for what we do in probability, and that's make decisions. We're really focusing on the idea of using data collection and that to help us make better decisions. So if there's probability involved in statistics, then a good understanding of probabilities would help us make better decisions. Now, uh, if you roll a coin, let's say you flip a coin. Let's talk about that. And there's been a lot of classical problems throughout history that people talk about, and I'm going to shorten this one up a little bit. Let's just say that we saw someone flipping a coin, okay? And we were watching and recording what they came up with. So they flipped it and it came up heads. And then they flipped it again and it came up heads. So it's a fair coin. It's got heads and tails. Nothing wrong with the coin. And they flip it again and up, they say heads again and heads and heads. And they keep flipping it and heads, right? So 1, 2, 3, 4, 5, 6, 3, 6, 7, 8, 9. Now here's a question. We just saw someone flip a coin 9 times in a row, and it kept coming up heads. So if somebody asks us the question, what's the probability of getting heads now on this coin toss? And a lot of people would right away, they would say, oh, it's 50-50. And that's where the controversy starts. Because is it 50-50? And people start to say things like, well, there's only 2 things it could be. That means it must be 1 out of 2, right? So but that's what we refer to as when we talk about a classical approach. Okay, classical approach of probability basically says that previous outcomes do not matter. Okay. And that's what you're saying when you say, oh, this is 50-50. What you're saying is that none of this has any bearing on what's going to happen right here on this particular coin toss. Okay. So now someone might say, well, wait a minute. I always heard that, sometimes they talk about gambling. Right? If you're watching somebody play a slot machine or something, they used to always say, well, if somebody loses a lot, then go play that machine because that means it's going to be hitting pretty soon because eventually it's going to hit. And what that is that's referred to as a relative frequency approach. Relative frequency approach says previous outcomes do matter. Okay, so they're kind of opposite here how they look at this problem. One, classical was looking at thing in isolation, nothing else going on. Relative frequency saying, wait a minute, let's look back here and see what just happened, because maybe we can't separate this thing by itself. We have to look at all of this together as one big continuous trial that goes on, or event. And then Bayes, he mentioned Bayes before, because let's look at Bayes. What would he say? Bayesian approach. Well, Bayes is a little bit more realistic and says, he says, well, I can't ignore all that, but really, this is one event, So I look at both of these, and Bayes actually, his computations come from a combination of these ideas. One would say 1 out of 2, the other one would say 1 out of 1,024, and he would be in the middle there somewhere. And basically, some people believe in that, some people don't. And so you got these three different approaches. And we're not going to talk about which one's right or wrong. We want you to understand that there are different approaches and that people think differently about situations than you do. There's a lot of people that think this would be 1 out of 2, but there's also a lot of people that think it's 1,000 out of 24, and there's also a lot of people that think it would be closer to 1 out of maybe 200. So let's go ahead and move forward on that. We're not going to spend really any more time. And what I want to do is talk about, though, again, not the probability, but the statistics that comes out of this. Well, there were some mathematicians that looked at that. They thought, hey, could I figure that out mathematically? Is there a way to get an advantage to see what might be coming up on that coin toss? And so this one a mathematician, not a statistician or probabilist, he was a mathematician, and he took a coin and he flipped it 10,000 times. Okay. Now, he wanted to see, was there any kind of patterns? Because in mathematics, we like to look at patterns. When we see something that repeats, we try to figure out, what's going on? Is there some way we can maybe inductively prove this or come up and show pattern recognition, even if it's a very big pattern? But this mathematician looked and looked and looked and looked and came up with nothing other than this. And he said that, well, there's one thing I can tell you about the results of this experiment is that when I was done flipping 10,000 times, it came up 5,000 times heads and 5,000 times tails. So the idea of this law of large numbers is important in statistics. Okay, law of large numbers. Law of large numbers says as you increase the number of trials in any given experiment, you will approach the true theoretical probabilities. And nobody argues that. Even though we have three different types of people thinking about probabilities, right? Three different thought processes and probabilities, none of them are arguing and saying, well, no, this is not true, right? We all kind of agree on that. And this was a good experiment to show. But there's one other thing that people, some begrudgingly, also agreed to was that there are no single event probabilities. So that question I asked you before, no one's ever been able to prove one way or the other throughout all history, and mathematicians and probabilists and that. We have no one that can prove one way or the other what the answer is. And that's because of this right here, because there are no single event probabilities. Okay. We have no proofs. No one been able to show that we can tell exactly what's going to happen on a coin toss on any given single trial. We just know what's going to happen in the long run. Okay. And we had to first assume again that it was 50-50, heads and tails were 50-50, and that it was a fair coin and so on. And so let's go ahead and again, we're going to move forward into some other stuff. Let's clear this out. And what are some other things that we do agree on as we move forward in statistics? Well, probabilities, and I'm going to write it as P of X, right? Probability, right, is going to be a number between 0 and 1. So when we write probabilities, we might say, oh, 1/2 could be a probability, 1/3, 0.2, and things like that. So we can see fractions or decimals, but these numbers are not negative, and they're not greater than 1. So we couldn't have like 1.5 as a probability, right? That's not going to work. Negative 3.8 is a probability. No, no, they're numbers between 0 and 1. Okay. And also, everybody kind of agrees on the sum of the probabilities, and I could X is going to add up to 1 in a given experiment. All right, so what does that mean? This is sum, it's sigma, summation, and it's saying that if I have a coin, okay, flip a coin one time. So we're talking about that coin toss again, right? And we write out the sample space. What's the sample space? Again, okay, well, that's all the things that could occur. So the sample space is heads or tails. Every time we flip the coin, it's going to come up either heads or tails, okay? So we can agree on that. And then the sum of the probabilities. So let's say that we say that in the long run, the probability of heads is equal to 1/2. Probability of tails is equal to 1/2. And we got them both covered. So when we add up these probabilities, we get 1. Okay. So when we look at, no matter how many things are in our sample space, each one will have a probability that is between 0 and 1. And when we add up all of their probabilities, they will add up to 1. Okay. All right. So let's look at that a little bit more. Let's say that we're going to roll a die one time. Right. All right. So let's write out the sample space. So this is going to be again a fair die. All the numbers are going to be equally likely to occur. So the die has numbers 1 through 6. And just like a board game die, and those things have been around for a long time. The ones we typically see are, again, 1 through 6. So if I wanted to say, hey, what's that long run probability or theoretical probability of a 2? If I roll it one time, odds of getting a 2, 1 out of 6. Because there's 1. This 1 is representing how many things that we have of those in our sample space. And there's 1 right there. Right? There's 1, 1, 2. How many total numbers are in our sample space? 6. So that's where we get to. In fact, they all, right? All those numbers, probability of a 1, 1 out of 6, probability of a 2. Again, they're all equally, that's what we mean by equally likely. 3, 1 out of 6. And what do we got? Oh, we already have a 2 in there. We did that. Probability of a 4, 1 out of 6. Probability of a 5. So we got 1, 2, 3, 4, 5, and one more. Probability of 6, 1 out of 6. So when we add those all up, 1, 2, 3, 4, 5, 6 out of 6. So there's our sum. All of these numbers are numbers between 0 and 1. And again, it's kind of, not very exciting yet because we're just doing very basic, and these are all equally likely. Okay. So let's say that we wanted to look at something more involved. So we'll take it slow, steps at a time, right? We're just gonna, instead of working with numbers, let's just do one example with some colors or something. Let's say we're going to select one coin, okay? We want to know the probability of a blue coin. Okay. Now let's write out our sample space because we don't know what the probability is. This is different, numbers and all that. It was easier to figure that out. But a blue coin, what's the probability of a blue coin? Well, I don't know. Let's see. Depends how many of them we got in there. Let's say we had a red coin, green, green, and then we had a blue and a blue. So these are just coins. They're not like, anything funny or weighted or anything. We're not flipping them or rolling them. They're just sitting in a bag. We're going to reach down in there and randomly grab one, right? So there's nothing associated with each one on an individual basis like we had over here. We said each one was equally likely. Well, in a way they are, because these colors, regardless, there's how many of them in there? Well, 1, 2, 3, 4, 5, 6, there's 9. So that means that each one of these has a 1 out of 9 chance of being selected. But we can't just say, oh, blue's a 1 out of 9 chance. Because there's over here, each number, we only had one of those numbers. This one, there's 2 blues. So we can't think about there's 9, everything's 1 out of 9. So we got to think, oh, wait a minute. It's how many of those things are in there. Okay, blue coin, probability of a blue coin. Well, we got to see how many blue coins are in here. Yeah, there's 2 blue coins out of the 9, right, that are in there. So that's going to be, right, our probability of a blue coin is going to be 2 out of 9. Okay. So again, a little bit, we're adding a little bit to this. Now, let's say I wanted to add a little bit more to this. Right? We're going to stick with this, right? I'm going to erase, if I can get this up here. Is this working? Yeah. All right, we're going to take this out of here. Oh, if I press a little harder. Okay, so we got that. No. So let's say that the question changed a little bit. Let's say that we had the probability of a blue, I'm going to abbreviate blue again, B, or a green. Okay, so that's a little different problem. Again, I'm just kind of adding to the different types of problems that we could run into with even just a simple problem like this. And I see the word or. When I see the word or, right, we're looking for this one or this one to occur on one selection. We're still talking about one selection, this or this. So that sounds reasonable. That could be a problem, a probability problem. And it's just like saying we talk about the flu and all that stuff now. You could say, what's the probability of getting a headache or a runny nose, right? Because you might just get a headache, you might just get a runny nose. Sometimes some people get both, the headache, right, and a stuffy nose. But in this case, we want to know what's the odds that they had a headache or a runny nose and stuff. And so we could come up with lots of examples of where to apply this. But let's go back to this. So we're going to select one coin, right? Blue, red. So what this requires is something we call the addition rule. Okay. Addition rule. When you see the word or, right, that's going to clue. That's your clue. On a single selection, blue or green, then we got to kind of look at this. So what does addition rule mean? Well, we have to, let's do a problem, then I'll kind of add over here another thing. But the addition rule says that we would look at probability of a blue plus probability of agreeing. Okay. So how do we do that? Well, we can count, like, right, probability of a blue is where we just found that. That's 2 out of 9. Plus probability of a green, 1, 2, 3, 4 out of 9. Right? 2 plus 4, 6 out of 9. We can reduce. We're not going to reduce. We'll just leave it there for now. Okay. So this worked very well. In fact, the addition rule is very easy. When the events are mutually exclusive. Okay. What do we mean mutually exclusive events? Well, mutually exclusive means that things that cannot occur at the same time. Okay, we're talking about things that cannot occur at the same time. So what that means, let's go back over here. Oh, here's a problem. And can a coin be blue and green at the same time? Do we have any coins over here that are blue and green at the same time? No. So that means blue and green are mutually exclusive. We just add up, count up how many blues there are in green. And of course, the addition rule means to add. That's how we got our numerator in that case. So pretty straightforward. Now, let's do another example here. Let's take it. I'm going to clear that whole thing out and do another example. All right, let's say that we are going to look at the last digit of your phone number. What could the last digit be? I don't know. Let's write out the sample space. Could be 0, 1, 2, excuse me, 3, 4, 5, 6, 7, 8, 9, right? That's it. It could be anywhere else. So your last digit of your phone number is one of those. So let's say, all right, probability of getting a 4. So let's randomly pick someone. And what's the odds that their number is going to be a 4, the last digit? Well, that's pretty straightforward, right? This is what we refer to as a simple event. Remember, we talked about simple events that can't be broken down any further, right? So the 4, that's it. We can't break 4 down any further, probably. So this is 1, 4 up here out of the 10 numbers that are up there. So that's pretty straightforward. What if I ask, what's the probability that it is a 2 or a 7? Okay, it's not simple anymore. It's a compound event. Can this be broken down? Well, yeah, it could. Right, we can break this thing apart. It's a compound event. In fact, we want to break it down into 2 simple events and add. So we could take the probability of a 2 plus, because again, the OR tells us, right, probability of a 7. Here, now we have 2 simple events. We could say a probability of a 2 is 1 out of 10, plus probability of 7 is 1 out of 10. These all are 1 out of 10, right? They're all equally likely. And we're just going to assume it. And we come up with 2 out of 10. So again, that's nothing new, right? We're just throwing some stuff in there. But I want to add, all right? I'm going to add a little complexity to this. So let's keep the same sample space. Oh, let me back up. Are these things mutually exclusive? What does that mean again, mutually exclusive? They cannot occur at the same time. So can we have a last digit of a phone number and it be a 2 and a 7 at the same time? No. Okay, so they are mutually exclusive. Now, let's try this. Let's say that you have probability of getting an even number or less than 6. Is this a simple event? No. Is it a compound event? Oh, yeah. And it's got that or in there. So we know we could use the addition rule. Let's just see. Probability of even plus probability less than 6. How many even numbers are up here? 5. How many numbers are less than 6? 1, 2, 3, 4, 5, 6. 6 out of 10. That's equal to 11. Something's not right. Why? Well, remember, we said probabilities have to be a number between 0 and 1. This one's not. We definitely made a mistake somewhere. All right. Where did we make the mistake at? All right, let's go back. Let's back up. We were working with simple, compound. We did the addition rule. And we did not ask ourselves, are these mutually exclusive events? Okay. Are these mutually exclusive events? Can you have a number that's both even and less than 6? Yes. So that means these are non-mutually exclusive events. All right. So what we have to do is add in a little thing to this formula that we've been working with, and I'll write the formula in a minute. We have to subtract off all those numbers that satisfy both conditions. Probability of even and less than 6. All right, let's go over here. Even, less than 6, even, less than 6, even, less than 6. 1, 2, 3, minus 3 out of 10. I have 11 minus 3, right, or 8 out of 10 would be our correct answer for this probability of getting an even number on your last digit of a phone number, right, or less than 6. So what's the real rule here? Well, probability of A or B is equal probability of A plus the probability of B minus the probability of A and B. Okay, that's A and B. That's the addition rule, right? The full-fledged, whether you have non-mutually or mutually exclusive events, this is your addition rule, okay? And we're going to actually stop there and then pick up in the next video with another rule, but this will cover us for what we need. And I just want to go back over to the textbook. And again, we talked about these 3 approaches. Remember the 3 approaches, the probability. And we talked about the law of large numbers, right? And then that says numbers, right, as the number of trials increase, we'll approach to true theoretical probabilities. And we came up with some examples of those. Now, the complement I'm going to get to in the next video. So don't worry, we didn't forget about that one. It's going to fit into the next lecture on that. And odds, we'll pick those up at the end too. So if you're looking through a particular book and you see those, then that kind of ends the first section. And then I'm going to jump over to 147. Okay. So in the next section is where we picked up the addition rule. So we did most of 4.1 and we did the addition rule, and you'll see the addition rule I just talked about and finished up with right there. So now you know what that's all about. All right, we saw some examples, and so maybe it shouldn't look as scary as it initially might have. And we talked about disjoint events or mutually exclusive, right? Mutually exclusive. He calls disjoint, but we like the term mutually exclusive. And again, we'll get into complements and that. So we're going to finish up a couple things in there with complements. So we'll pick it up in this section, and then we're going to get into the multiplication rule. So we'll see on the next video.